Earth's climate is dynamic and formed from many different yet interlinked cycles and processes. This means that a multitude of factors affect how the climate changes, making modelling a complex process. In the past, gradual changes to one or more of the different cycles have led to butterfly effects that have resulted in large global climatic shifts. By looking back into the Earth's history, we can study the impacts these small changes had on the early Earth's global climate in order to better model how changes seen today can affect the climate. Evidence of these changes can be found within the geological records that we have extracted from sources including sediments, ice cores and fossils. The information within these, such as isotopic ratios, can be used as proxies to infer previous conditions. One of the most heavily researched climate proxies is the stable isotope oxygen-18. By comparing the ratio between oxygen-18 and oxygen-16, the most abundant form found on Earth, it's possible to calculate the atmospheric temperature of the past. But to understand how this is possible, we first need to know what influences the ratio between these two isotopes. Oxygen-18 and oxygen-16 are located in corals, marine fossils and polar ice. The common factor between these sources is the presence, at some point, of water. Water that incorporates the heavier oxygen-18 isotopes condenses more readily than water that incorporates the lighter oxygen-16 isotopes. This occurs as the heavier water has more mass due to the added neutrons in the oxygen-18's nucleus. The atmosphere can only hold a certain amount of water vapour, and this is dependent on the temperature. The hotter the atmosphere, the more moisture it can hold. The more moisture in the air, the larger the volume of precipitation. Large-scale ocean circulations, such as the thermohaline circulation, drive warm ocean currents towards the polar regions, such as here in Alta in the Arctic Circle. This carries along with it the water vapour. Due to lower pressures and cooler temperatures at the polar regions, water vapour condenses, falls as precipitation and then freezes and compacts as ice. This means that because oxygen-18 condenses preferentially, in a hotter climate there will be comparatively less oxygen-18 as it will have fallen as precipitation prior to have arriving at the pole. For practical reasons, the difference in oxygen-18 between the ocean standard and the source is used. This is known as delta oxygen-18. The equation we see here describes the relationship between the delta oxygen-18 found in the source, such as an ice core, and that found in the ocean. As this is often a small number, this relationship is multiplied by 1000 to give an answer in parts per thousand, or per mil as it's also known. 1 per mil of delta oxygen-18 corresponds to a temperature difference of around 1.5 to 4 degrees C. But what actually causes a temperature rise, as shown by our oxygen isotopes? Well, there are many factors that can contribute to a global temperature rise, but perhaps the most famous of these is carbon dioxide. You've probably heard about it on the news, how fossil fuel emissions are releasing trapped carbon dioxide into the atmosphere. But there's more to this story than the human impact, and it's a story that's being etched into the rocks of Earth and humanity's history. Fossil fuels aren't the only source of carbon dioxide on the planet. Carbon is one of the most abundant elements on Earth and is constantly transferred into different forms through the carbon cycle. In the atmosphere, carbon dioxide acts as a greenhouse gas and contributes to global warming, which increases the Earth's temperature. The carbon cycle is a system by which atmospheric carbon, such as carbon dioxide ejected by volcanoes, is fixated by organisms like plants, algae and cyanobacteria through photosynthesis. Once the carbon is fixated, it can be released through respiration at some point along a food chain, thus releasing the carbon dioxide, or it remains within the organism's harder proteins found in the skeleton. After death, this can then be petrified and turned into carbon-containing rock. Life prefers the carbon-12 isotopes, as they are more energetically favourable in the biological reactions, such as interactions with pyruvate dehydrogenase, an enzyme used to generate NADH in both plants and animals. Therefore, a higher primary productivity would withdraw more carbon-12, which in turn leads to more carbon-13 held within rocks rather than organic matter.
Looking at the rock records on the ocean floor, we are able to determine the ratio of carbon-12 to carbon-13 throughout geological history. By comparing these ratios from the different depths of a sediment core, we can infer how productive the biosphere was at different points in Earth's history. A common rock used in carbon proxy research is limestone, which has a chemical formula of CaCO3. The amount of limestone in the oceans is mediated by a process called carbonate weathering. To investigate this process, we went to the University of Leicester. The process occurs as follows. CO2 is supplied to the atmosphere by volcanic and metamorphic emissions. Atmospheric CO2 forms carbonic acid when it dissolves in ambient water vapour. This falls as acid rain, which erodes carbonate rock and releases more CO2. This reaction can be shown using a piece of limestone and a strong acid. Now, we don't have carbonic acid available, but hydrochloric acid can be used as a substitute. The products of this reaction will include solutes such as calcium ions and bicarbonate ions. In practice, these ions are carried to oceans by rivers where CaCO3 is formed by calcifying organisms and organic matter, thus taking carbon out of the atmosphere, reducing the greenhouse effect and lowering global temperatures. Weathering is sensitive to changes in climate. In general, it is faster when the climate is hot and wet, and slower when the climate is cold and dry. Carbonate weathering not only has implications for global temperatures, but also impacts several historical man-made structures. Here in York, we're at the famous Minster Cathedral. The rocks used to build the cathedral are predominantly limestone. If you look closely, you can see significant evidence of weathering caused by acid rain. This occurs at such an extent that by the time the stonemasons have finished replacing the corroded limestone, it will be time to start all over again. We have now looked at how geologists have come to understand temperature and productivity of the past through oxygen and carbon isotopic evidence respectively. But the story doesn't end here, and there is a myriad of different proxy evidence that can be used to understand our past, present, and future.